Hey everyone, in this video we're finally going to learn how to analytically integrate functions, basically how to find the area underneath them without actually drawing them out. So one of the consequences of the fundamental theorem of calculus that we talked about kind of over the last couple videos is that if you are taking the area of a function between 2 points, well, you could come up with a new function which describes how much area between wherever you start and an unknown finish point. Well, if you do know the finish point, then you could figure out the area over that interval by just using the area function between 2 points. And one of the other consequences of the fundamental theorem of calculus is this area function is nothing more than just the opposite of the derivative of the original function. So we'll call this anti-deriving because it's literally just deriving but going in reverse. So if you want to find the area underneath f between b and a, you just have to figure out what is the antiderivative of little f, and we'll represent that with big F, and then evaluate it at the 2 points. So I have a whole bunch of the, well, maybe not a whole bunch. I have a couple of these for us to think about. And honestly, just like with derivatives, just like with factoring, some of that other stuff, it just takes a bunch of practice to get used to thinking about these backwards. So here's my first integral here. I want the area between 1 and 3 of the function x to the 5 halves. So what I want you to think about is if you were going to derive this, so maybe you don't write this down in your notebook, but if you were going to derive this, what would you do? You would use the power rule. You would multiply x by the original exponent, and then you would subtract 1 from the exponent to make the new one. So if we're anti-deriving, I want to do that in the exact opposite way. I want to do everything there exactly backwards. So first thing, the last thing we did was we subtracted 1. Whoops, sorry. The last thing I did was I subtracted 1 from the exponent. So if I'm going to use the power rule in reverse, the first thing that I'm going to do is I'm going to add 1 to the exponent. Now it's in halves, so I have to add 2 halves. So that would give me 7 halves. And then the first thing I would do if I was deriving is I would multiply by the original exponent. Well, now I'm going to divide, because that's the opposite of multiply by, right? I'm going to divide by the new exponent here, which you can clean up to be 7 halves x to the 7 halves. If you don't believe me, just derive your answer. So now let's take a look at this guy. If we were to derive this, well, I would, oh no. You know how sometimes you just your brain gets ahead of your mouth? Well, I said divide by the new exponent, and then I divided by the reciprocal, because when you clean it up, you take the reciprocal. So I'm sorry. Here we go. My bad. Here we are. And hey, like I said, if you don't believe me, take the derivative. Here's how you check your answer. Derive your answer. What would we do? We would bring down the exponent, so it would have 7 halves times, just bring your coefficient along for the ride, 2/7, times, now subtract 1 from the exponent for the power rule, 5 halves. Oh, look, 7, 7, 2, 2. I'm back to where I started, so I know I have the correct antiderivative. But all I've done here is I've come up with the antiderivative. This is my capital F of x. I want to show you 2 different ways that are acceptable to finish solving this problem. Just you pick whichever way is your favorite. It's the same amount of work, it's just a different way of notating it. So what some people will do is they will say capital F of x equals this, because it's the antiderivative. And then you would say, so the integral from 1 to 3 of x to the 5 halves dx equals capital F of, so the area function evaluated at the upper limit minus the area function evaluated at the lower limit. And then you go ahead, you plug in 3, you plug in 1. So that would be 2/7, 3 to the 7 halves minus, well, that would just be 2/7 times 1. You can clean this up, but don't. Again, we're really here just to work on the calculus, not the arithmetic, right? So that's one way people will do this. It really doesn't matter. Here's the other way you could notate this. Instead, so you're doing your integral, right? It was 1 to 3 x to the 5 halves dx. You can say equals, then let's come up with the antiderivative. So we found it was 2/7 x to the 7 halves. But you can't just leave it here, right? Because that's not true. You can't forget about the 1 and the 3. Remember, AP hates it when you falsely equate things. So what we do is, and you may have seen me do this a little bit before in our other classes, remember a vertical line after an expression means evaluated. So if I put 1 here and 3 here, this means evaluated at 3 and 1, and then of course you're going to subtract. Because you're still indicating, hey, here's my upper limit to evaluate, here's my lower limit to evaluate at. So really it's just a different way of replacing this line right here. And then at this point, start substituting in. So plug in your upper limit first, 2/7, 3 to the 7 halves, minus 2/7 times 1. Either way, get the exact same thing. You will see me do it this way more commonly, but sometimes it's helpful to do it this way, especially like in context problems, like in word problems. You'll see me start to do it this way sometimes. I'll just explain when we get there. Okay, so I know I took a lot of space there, but we have the rest of the page for the other two. So let's see. For our next one, we have 2 plus cosine of x. So let's see. Well, and just in your mind's eye, this is one we could kind of visualize, right? In your mind's eye, we know the cosine function normally does this, right? But if we shifted it up 2, okay, well now its midpoints would be at 2, its mins would be at 1, its maxes would be at 3. So it would do something like this. So you could find the area underneath it with like a rectangle and then something that would figure out this curve shape. Or, you know, we could just use the integration evaluation theorem. Dun, 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 dun. So let's see. Let's ask ourselves how we would do this in reverse. Remember, you can split integrals along addition or subtraction just like how you can split limits, just like how you can split derivatives. So let's integrate from 0 to pi over 2 of 2 dx plus integral from 0 to pi over 2 cosine x dx. Do you have to do this every time? No, I just want you to think about the antiderivatives individually because it's a little bit easier. Okay, so what would I have to start with if my derivative is 2? I think I'd have to start with 2x, because if it's linear, then when I use the power rule, the 1 would come down, doesn't do anything, and then the x would go away because I'm subtracting 1 from the exponent. And so I'm actually going to combine these back together, but I separate them, so I wanted you to think about them separately. If our derivative is cosine, the thing we started with, in air quotes, the thing we started with must be the antiderivative of cosine, which would be coming back to sine of x. And then again, I'm going to indicate that I need to evaluate this in 2 places, pi over 2 and 0, and then I'm going to subtract them. So let's do that. What do we have? So we have 2 times pi over 2 plus the sine of pi over 2. Remember when I told you the unit circle never went away last year? I meant it. There's my first half. And now I've got to do the same thing. I've got to plug in 0. So 2 times 0, well, that's 0, plus the sine of 0. And if we clean this up, let's see, 2 and pi over 2 would leave me with a pi. The sine of pi over 2, let's see, pi over 2 is up here, cosine sine, so the sine is 1, minus 0 plus the sine of 0 is 0. Okay, so our answer then is pi plus 1. Huh, interesting. Well, you know, with the rectangle kind of would have made the 1, right? And then or would have made the pi. I don't know. Not important. again, oh, and by the way, if you wanted it to notate it the other way, that would be totally fine. Basically, you need to say, come on, scroll please, thank you. You need to say somewhere, oh, my antiderivative f of x is, and then you'd say 2x plus 1, or 2x plus sine x, I'm sorry. And then you would do f of pi over 2 minus f of 0, just like we did down here. Then you get to this line, then you get to the final answer. You know, whichever way you want to do it, whichever way feels cleaner to you, more elegant to you, go for it. I'm going to copy this last one below the page here because I'm just fat fingering this and writing really big. So let's see. This one goes from -5 to -3 of x squared plus 1 over x plus 1 dx. And again, in your head, you don't have to do this on the page, but in your head, I want you to think about this like it's two separate integrals, because then it's going to help you antiderive it. Some people just separating it really helps folks figure out the antiderivative, because now it's like, oh, I need an antiderivative of x squared. I need an antiderivative of 1 over x plus 1. Let's see. So here, I'll do it the other way first. Since I did my favorite way the second way, I'll do the other way this time. My antiderivative would be, let's see, I have to undo the power rule. So remember, instead of deriving where I'd bring the exponent down and multiply, instead I need to add 1 to the exponent and then divide by the new thing. And then, oof, this other one. What to do with this other one? It's 1 over stuff. Well, let's just take a brief aside. If it was 1 over x, maybe this would be easier to think about than 1 over x plus 1. That's one of the things that would show up on your derivative rule card. If you work backwards, that would come from the natural log of x. The derivative of natural log of x gets you to 1 over x. So then the antiderivative of 1 over x should get you back to natural log of x. How is it different when we have the plus 1 in there? Well, it's really not. I'm just going to stick the plus 1s in here, and then it works out. If you don't like that, on your derivative card, I intentionally chose u instead of x, because then you can make a little substitution here. Whoops, u. So the actual rule looks like this. Derivative of natural log of u gets you to 1 over u. And before this, you could say, let u equal x plus 1. Well, then that would mean the derivative of natural log of x plus 1 would give you 1 over x plus 1. So we should be able to go backwards for our antiderivative. I hope I'm not going too fast or too slow. This is honestly one of the lessons that I normally prefer to teach in person, just because it's a lot to think about and people pick this up at different speeds. So hopefully I'm doing a good job, I guess. So let's see, our antiderivative here would be natural log of x plus 1. Now, I am actually just going to throw a wild card at you. This sounds right, this looks right, and I'm just going to tell you, I do have one modification to the natural log rule, and we'll get that down on your derivative card. We'll talk about it a little more in the future. We'll talk about why this rule exists in the future, but for the sake of discussion, when you antiderive, it actually slaps an absolute value on here instead of a set of parentheses. Small thing, but people forget it all the time, so I wanted to start training you early. Okay, so there's our antiderivative. Now let's evaluate it in the two places. Whoops, didn't mean to do that. Oh well. Here, we'll just say capital F of x equals this. So then our area would be f of -3 minus f of -5, which would be -3 cubed over 3 plus natural log of, well, the absolute value of 4 is 4, so you don't necessarily need the absolute value here. There's our first part, and then our second part minus, start all over again, we'll plug in -5. So I'll cube it, divide it by 3, plus, now the absolute value does matter here because -5 plus 1 is -4, so the absolute value of -4 would just get you back to +4. Wait. Oh my goodness. I made a mistake. I made a mistake. I'm making a mistake. Oh, everywhere. Hey, did you know -3 plus 1 is obviously 4? Because that's what I said it was. It's not. It's -2. So then the absolute value would matter back here as well. I'm sorry. So this is just going to be 2 and then 4. At this point, it's just cleaning it up. You can probably leave it like this. If you condense it, if you want to condense it, you'll get all the way down to -98 thirds plus, nope, minus the natural log of a half. Ugh. Is that any better? No. This is probably fine. At most, I mean, these are thirds, so I could see putting them together. Here's a natural log, here's a natural log. So I could, maybe we should at least like do the simple stuff. But for today, really what I just want you to focus on is getting to this step. And then we can worry about the other stuff in the future. Minus natural log 1/2. Whew. 16 minutes on 3 problems. Not doing so good, are we? Well, it's hard stuff, I think. This is huge. This is what Calculus B is all about. Like I said, it's all about area. Hey, we just figured out how to evaluate areas. Pretty cool, huh? Yes, Mr. Doolin, it's the coolest thing I've ever seen. Okay, let's turn the page. Okay, everything we've done so far finds in the total amount of net area. What that means is area above the x-axis is considered positive. So function is positive above the x-axis. And then area below the x-axis comes in negative. So if you did happen, and I think we talked about this in another video, or some people asked me about it in class. But yes, if you had you know, a function that does this, you would get negative area for the integral over here, and then you would get positive area for the integral over here. That's considered, if you add those together, that's considered the net area. Well, sometimes, what if we just want the total area? What if we do want to treat this as positive and this as positive as well? That's what we're going to do next. Great news. It's very easy. Total area, well, let's just treat the negative area like it's positive. There's a couple ways you can go about this. If it's an easy function like this guy, hey, y equals mx plus b. That's a linear function. I can graph that. Let's see. We're in the negative region. It's got a slope of 1 and a y-intercept of 2. And then we're going all the way back to what? -5, which the y value there would be -3. So if we were to find this area, well, you could just say, I'm going to find this area and then make it positive. I'm going to find this area, keep it positive, I'll add them together. Something else you could do is you could, when you integrate the absolute value of the function from -5 to 0. And because this function was linear, well, now it's just an absolute value, so it's just going to make that V shape that we're used to, right? And then you'll have, again, your two triangles. This one that was red in the area is now going to be still red over here, positive area. This, what was blue, what was originally positive, is still going to be blue. And still a pair of triangles, you can still find the area. But not every function is that simple, right? This one was only really simple because it was a linear function which flips to an absolute value, which is something we know what that looks like. What if it's something that we don't necessarily know what it looks like? Here's what you can do. You can look for wherever the x-intercepts are. So in this case, the x-intercept is at -2 and 0. And wow, hey, that's the end of the school day. What do you know? Split the integral there, because you really only need the absolute value of the part that's negative. And so really, I could take, if I want the total area, what I could do is I could say, well, I was going to integrate from -5 up to 0 of x plus 2, but I want the total area, right? Let's break it into parts. Let's take the area I know has to be negative. That would be from x is -5 all the way until x is -2. I know that area is going to come out negative, so I'm going to put the area or the integral inside the absolute value, because now that'll force it to be positive. plus then we'll do a regular old integral from -2 until we get to the endpoint. Because this area is going to come out positive. I don't need to absolute valuefy it. It's already positive. In this case, so again, why am I showing you this? In case we can't use geometry to get there. Then I would still find that antiderivative. Good news, the antiderivative is going to be the same because the inside of the integral, hey, that's called the integrand, by the way, if you care. The inside of the integral is the same. So the antiderivative is going to be the same. My antiderivative is going to be, let's see, power rule here. So from x, I would have to increase the power by 1 and then divide by the new exponent. And then for 2, well, the x will appear. For any constant, the variable will appear. So let's, how do I want to do this? Well, we'll just keep going. I'll leave that there. That's my antiderivative. So let's evaluate this at these 3 places. Why'd you say 3 and then circle 4? Because -2 is the same. Okay. So I've got the absolute value of x squared over 2 plus 2x, evaluated from -5, it's -2. And then I've got to make sure that's inside the absolute value, right? And then plus x squared, behave. There we go. And then from -2 to 0. So it looks like a lot, but none of it's hard, right? -2, I'll square it. And you might be thinking to yourself, why didn't we just do triangles? Again, you could do triangles for this one. I'm just trying to show you for that way if you had to do something that was more complex, you could do it. Minus, okay, now I'll plug -5 in here. Squared over 2 plus 2 times -5. Okay. So there's my first one. There's my part that gets absolute valued. And then plus my part that doesn't have to be absolute valued. Oh, and nice. I'll be plugging in 0 first. So 0 squared over 2 is 0. Plus 2 times 0 is also 0. Minus, and then -2 squared over 2. Ooh. Looks like a lot, but let's see. 4 halves plus, well, that's really 2, right? 2 plus -4, and then 25 halves minus 10, which would really be minus 20 halves. So this would be minus 5 halves overall. And then what do we have over here? Minus, so this would be another 4 halves, so that's 2 minus 4, so minus -2. Oof, okay. 2 minus 4 minus 5. The computer's needing to restart. Or I say this was minus all of this, so it would be -2, so plus 2. Let's see, will these take care of each other? Nope. Dang it, I made a mistake somewhere. It's supposed to be 13. All right. I know this is the correct answer. I know I've missed something somewhere. And I have a meeting to get to in 4.5 minutes, so I don't have time to go looking for the answer. And I also don't want to re-record 24 minutes of video. So I'm relying on you guys to tell me tomorrow where I screwed up. I'm sorry. We should have just done triangles, obviously. Moral of the story, if you can do triangles, I guess. Hey, before I get out of here, I do want to show you one that's more complex. So, like I said above, if you can split it apart at any 0. But if you are allowed, just use your calculator for this. If you want the net area on your integral, just put the whole thing on the inside in an absolute value. Yeah, this graph looks whack. Like seriously, here it is in Desmos. Here's the regular, it's a cubic function. Okay, so that kind of looks like how we would expect it to. The absolute value graph is fun. It looks whack because, you know, it's flipping over in the areas where the original one is negative. But that's no problem for your calculator. So let's do it, and then I gotta run to that meeting, and I guess I'll have to make another video for the last page. Let's see, what was it? It was from -1 up to 4. And then remember the absolute value function you can find in this button right next to 9. And it's this option in the second row. Yes, put it in, please. Thank you. All right. X cubed. And then we got to close it with the dx. Hey, see, it was no problem at all for this guy. All right. Sorry, guys. I'm going to have to make another video for the last page, I guess. Sorry I went long.